Okay, hello. So at this point I would like just to do a few examples showing properties of logarithms. So at the end of last class we've covered these three major laws: the product, the power, and the quotient rules. We did go over change of base formula, and we did discuss the basic four properties of logarithms. Now I just want to do a bunch of examples just showing how to use all of these. Okay? So here's a first example, first set of examples. We're asked to express as a sum of logarithms. So what I see here, I see a log base 3 of a product. So that looks like a product rule. Based on the product rule from a previous page, I can split this into log base 3 of 81 plus log base 3 of 27. So actually I'm done. I just completed the assignment. I can actually take this further because log base 3 of 81 would equal to 4 because 3 to the power 4 equals 81, while log base 3 of 27 equals 3 because 3 to the power 3 equals 27. So this expression actually equals to 4 plus 3 equals 7. Similar situation here. I see a log base 4 of a product. Therefore, I can use a product rule. Based on the product rule, we can split the product into a sum of logarithms. So that's log base 4 of 64 plus log base 4 of 4. We can take this further. 4 to the power 3, I believe, is 64 because 4 squared is 16 times 4 is 64. So log base 4 of 64 equals 3, and log base 4 of 4, to what power we need to raise 4 to get 4? That equals to 1. So 3 plus 1 equals 4. Now here, all we have is natural log of x times y. So again, it's a product that becomes natural log of x plus natural log of y. And there's nothing else we can do about that. Okay? So it's pretty much just using the product rule. You start with a single log of a product, and you end up with the sum of logs. Okay. Now here we're asked to express as a product. So what I see, this is log base. This is log base b. That's b of 2 to the power 3. So that's a power rule. When you have a logarithm of an exponential expression, we can bring the power down. So that gives me 3 times log base b of t. So that's it. Now that logarithm is expressed as a product. Same thing here. We have log base c of k, and k is raised to the power negative 6. Therefore, by the power rule, we can bring negative 6 down, and then we're left with log base c of k. Now in the last one, when we have a natural log of a square root of a, we actually have to remember that a square root can be expressed as the power 1/2. Radicals are fractional exponents. So here we can use the power rule again and bring 1/2 down, and that leaves us with natural log of a. Alright? So that's just all those three examples. We're using the power rule. The power rule suggesting if you have a logarithm of an exponential expression, the power can be brought down. Okay. Here are a few more examples. Express as a difference. So that's just using the quotient rule. When you have a logarithm of a fraction, of a division, just like with the exponents, we will subtract the logarithms. That becomes log base t of m minus log base t of 8. And that's it. So here's a single log expressed as a difference. Similar situation here. We have log base a of 76 over 13. Again, using the quotient rule, this can be split into a difference of logarithms. Log base a of 76 minus log base a of 13. Okay, so these are pretty straightforward. Again, remember, you're watching a recording, so if you have to, you can pause or rewind or whatever you like. Okay, so now we're getting a little more complex examples. Here we have to express in terms of sums and difference of logarithms. So what I see in this first example, I have log base a of x cubed times y squared times z. So there are two products here. But again, I can use the product rule to split this into log base a of x cubed plus log base a of y squared plus log base a of z. So that just using the product. Now I can take it further. What I see in the first place here, I see log base a of x cubed. So that means I can apply the power rule and bring the exponents down. So it's 3 times log base a of x plus 2 times log base a of y plus log base a of z. And that's my final answer. Now we express it in terms of sums and difference of logs. Okay? Here's another example. What I see here is log base b of a big fraction. So the division is the main operation. That's what I'm going to focus on first. So that's the quotient rule. The quotient rule suggests if you have a log of a division, it can be split into difference of logs. So I'm taking the log of a numerator minus the log of the denominator, m to the power 4, b to the power 9. Okay? Now, I can take it further. The first logarithm is a product. It's a logarithm of a product, so I can apply the product rule to split it into log base b of p squared plus log base b of q to the power 5. And I can do the same thing with the second log, but I have to be really careful because there is a minus in front of it. So I will keep the sum in the parentheses. So that gives me log base b of m to the power 4 plus log base b of b to the power 9. On the next step, I will distribute the negative sign, so I'll end up with 2 negative logs. So you can actually take this as a rule that everything in the numerator will have a plus, and everything in the denominator will end up with a minus, because when I distribute the negative, both logs will have a minus in front. But again, I can take this further. I can bring the exponents down using the power rule. So the first log, 2 comes down, leaves us with log base b of p plus, here we have a power 5, 5 can come down, so that's 5 times log base b of q. Now distribute the negative times whatever this log is. I can bring the 4 down using the power rule, so 4 comes down, log base b of m, and then minus. Now I will look at this expression a little more careful. I have log base b of b to the 9. As you notice, the bases here and there match. If I refer back to my set of rules, when bases match, I'm just left with whatever the power was. And this should make sense in this case, because when I look at log base b of b to the ninth. The question is, to what power do we need to raise b to get b raised to the power 9? And the answer is just 9, so I'm just going to make it minus 9. Okay, and that's it. So this is getting a little more complex. And actually, we need to be able to manipulate these expressions in order to solve equations. That will help us tremendously in the equation solving part. Okay. So here's a similar problem, only it has a big fourth power root. So that fourth power root, the fourth root applies to the entire expression inside of the log. And again, if you recall what I said earlier, the fourth root of x, let's say, is the same as saying x to the power 1/4. So really, I have a big exponent here of 1/4 using the power rule. I can bring it down. So 1/4 comes down. And I'm actually going to start skipping steps here because, again, all I see, if I take the rule that I told you earlier about, that everything in the numerator will end up with a plus and everything in the denominator will end up with a minus, I can actually go ahead and break down this fraction into log base a of m to the power 8 plus log base a of n to the power 12 minus log base a of a cubed minus log base a of b to the power 5. So you see what I did? Everything in the numerator remained with a plus, everything in the denominator got a minus, with the big 1/4 multiplying the entire expression, because the fourth root was applied to the entire fraction. Okay, now taking this further, we can use the power rule to bring all the exponents down. So this is 1/4 times 8 log base a of m plus 12 comes down, log base a of n minus, well, here's another case where we have matching bases. It's log base a of a cubed. So using our rules, it just equals to 3. To what power you need to raise a to get a cubed? And finally, on the last log, 5 comes down, log base a of b. So technically, this is already the final answer. We can distribute the 1/4. If we do that, 1/4 times 8 is just 2, so that's 2 log base a of m. 1/4 times 12 is 3, so plus 3 log base a of n minus 1/4 times 3 is negative 3/4, and 1/4 times 5 is negative 5/4 log base a of b. Okay, but again, the main thing was to recognize the fourth root as an exponent, 1/4. So 1/4 came down as a power, and then we'll break down the fraction. Everything in the numerator ends up positive, everything in the denominator ends up with a negative. Okay, here's another example. I have a natural log of a cube root. Again, as it before, cube root can be interpreted as an exponent of 1/3, so 1/3 comes down. And then we can apply the product rule to split this into natural log of 5 plus natural log of x cubed. I'm sorry, of x to the power 5. Like that. So natural log of 5, I can plug it in my calculator, but I really don't want to. Natural log of 5 is natural log of 5. Unless you're asked to round it to whatever decimal places, you should leave natural log of 5 as it's written. And the only other thing that I can do is to bring 5 down using the power rule, so it's 5 times natural log of x. Okay? So these get a little more complex, but again, we're just operating with the rules that we talked about last time. Okay? Again, if you have to, you can rewind, and something is not making sense, please email me or ask me in class. All right, a few more examples. Now this is going backwards. Express as a single logarithm if possible. Now I think all of this will be possible, but so we're going backwards. So now what I see is the sum of two logs, and the key that the two logs have the same base. They must have the same base in order for us to utilize the product rule. The product rule tells us the sum of logs is a log of a product. So this becomes log base A of 75 times 2, which is 150. So that's log base A of 150. Done. But again, the key here is that all the bases are the same. If the bases are not the same, it won't be possible to put it into a single log. All right, here's another example. 1/2 log of A minus log of 2. So here I have this 1/2. I need to get rid of that. So I can use the power rule. If I see a constant in front of the logarithm, it can be put back as an exponent. So this becomes log of A to the power 1/2 minus log of 2. Okay, so now I have two logs separated by a minus. So that's the quotient rule. So I can rewrite it like this: log of power 1/2 is same as the square root, so that's square root of A over 2. Okay, I hope that's all right. So let's keep going. Now here, I can just use the order of operations. I can say do the parentheses first. So what I see inside the parentheses is, sorry about that. Okay, sorry about that, got a phone call. But anyway, so where were we? Order of operations. So do the parentheses first. So there is a minus in between. So we can use the quotient rule to rewrite it as natural log of x over y. Okay. Now, I have a sum of two logs, but the second log has a constant in front of it. So again, using the power rule, we can throw this constant back on top as an exponent. So it becomes natural log of 2x plus natural log of x over y, but the entire fraction has to be cubed because 3 is applied to the entire logarithm. Okay? Well, now it's a sum. Using the product rule, the sum becomes a product, so that's 2x times x cubed over y cubed. So again, if it's a product, the 2x entirely can go in a numerator. So this becomes natural log of 2x to the power 4 over y cubed. Okay? So now we got a single log out of all that. All right, good. I hope that's making sense. Again, we'll need these skills in order to solve equations. It's very important for us to be able to take several logs and put it into one. It will make our equations go a lot smoother. Okay, here's another example. Natural log of x squared minus 4 minus natural log of x plus 2. The main thing is the minus in between. So I can go ahead and use the quotient rule. So it's x squared minus 4 in the numerator over x plus 2 in the denominator. Okay? I can actually take this further because natural log of x squared minus 4, x squared minus 4 factors into x minus 2, x plus 2 using difference of squares formula divided by x plus 2. So I can reduce this fraction by x plus 2. That leaves us with natural log of x minus 2. And that's it. That's our final answer. Actually, we should realize that there is nothing I can do with the logs of a difference. I don't have a rule for that. Okay, we have a rule for natural log of a product or natural log of a quotient, but a natural log of x minus 2 is just natural log of x minus 2. There's nothing else I can do about that. Okay? All right, let's keep going. This is a very similar example. Again, I see a negative in between, so I will use the quotient rule. And again, the main thing here is that I have to make sure that logarithms have the same base. Here I have log base 10 minus log base 10, so I can apply those rules. So it's x cubed minus 8 over x minus 2. Just as before, x cubed minus 8 could be factored using the difference of cubes formula. You can review that formula later, but that should give you x minus 2 times x squared plus 2x plus 4 divided by x minus 2. So again, x minus 2 can cancel, and we're down to just log of x squared plus 2x plus 4. Nothing else can be done with that. We have succeeded in expressing this expression as a single logarithm. Okay. Now here's the last exercise in this set, as far as taking several logs and putting them into one. Again, I will stick with the order of operations. I have a big parenthesis with the minus inside. So I will use the quotient rule to put it together. So 2/3, and then it's natural log of x squared minus 9 over x plus 3. I still have that another log over here. I'll take care of that one later. Okay, as in previous examples, x squared minus 9 can be factored. So this is 2/3 natural log of x minus 3 x plus 3 all over x plus 3, and that log is still attached here, plus natural log of x plus y. So I can reduce this fraction by x plus 3. Okay, I forgot my constant. There's still 2/3 in front, so it's 2/3 natural log of x minus 3 plus natural log of x plus y. Alright, so now I can keep going. I see this constant in front of the log. It can be thrown as an exponent. So this becomes natural log of x minus 3 to the power 2/3. X minus 3 is raised to the power 2/3 plus natural log of x plus y. So here I have a sum of two logarithms with the same base. So I can put them together using the product rule. So x minus 3 to the power 2/3 times x plus y. So all of that is on the inside of that log. We can even take this further. The power 2/3, that's a cube root squared. So that actually can be written as a cube root of x minus 3 squared. The denominator is the root, the numerator is the exponent, so it's a cube root of x minus 3 squared times x plus y. Okay? So it's getting a little trickier, but again, we need that to solve equations. Just being able to combine several logarithms into one. Again, you can rewind this recording if you have any other questions. Alright, so here are a few more exercises. Okay, so this is actually fun. We can actually have fun with them. What is given to us that log base a of 2 equals 0.301, log base a of 7 equals 0.845, and log base a of 11 equals 1.041. Okay, so I really don't know what a is in this case. I mean, I can solve for a, but I'm not going to. It's irrelevant for this problem, because all I have to do is to evaluate log base a of 211. Okay, I don't know what a is, But I know what log base a of 2 is, and I know what log base 2 of 11 is. So I can use my laws of logarithms to split this into log base a of 2 minus log base a of 11. Now log base a of 2 is given 0.301 approximately, minus log base a of 11 is given 1.041. Okay? I can use my calculator to compute that. Just plugging this into my calculator, 0.0301, oops, 0.301 minus 1.041 equals negative 0.74. And it's approximately negative 0.74. That will get? Yes. Alright, and I can do all of them like that. This one is a little trickier. It's log base a of 98. Well, let's see. What do I know? I know log base a of 2. I know log base a of 7. So how about taking 2 out of that? It's log base a of 2 times 49, right? 2 times 49 is 98. So using the product rule, that becomes log base a of 2 plus log base a, well, 49. 49 is 7 squared. Well, that's lucky because I know what log base a of 7 is, and using the power rule, I can bring that exponent, that 2 down, so it's 2 times log base a of 7. Now I actually can compute, the rest of that, because log base a of 2 is given 0.301 plus 2 times log base a of 7, which is 0.845. I can plug it in my calculator at this point. 0.301 plus 2 times 0.845 equals 1.991. And that's it. Now the last one, log base a of 1/7. I don't know anything about 1/7, but I don't know what happens to log base a of 7. Now remember, the fractions can be expressed with negative exponents. So this is log base a of 7 to the negative first power, which means I can bring negative 1 down by the power rule and still leaves me with log base a of 7, which is given to be 0.845, 0.845 with a negative in front. So we're done with these exercises. So again, using the laws, we're able to express these logarithms in terms of what is known to us. Okay? All right. And then a few exercises in the end, just using the basic properties. Here we have log base t of t to the power really doesn't matter. Just remember what happens when the bases match. To what power I need to raise t to get t to the power 2713? Well, the answer is 2713. That's just using this property right here. When the bases match, you're just left with an exponent. Okay. Next one, 5 to the power log base 5 of 4x minus 3. So again, this is one of those inverse properties. The bases match, so we're just going to be left with 4x minus 3, whatever's on inside that logarithm. So again, it's using one of those properties on the list. This property right here. If you have an exponential expression where exponent is a logarithm and the bases match, we'll be left with whatever inside the logarithm. Same thing here, e to the power natural log of x cubed. Natural log is base e, so just like in the previous example, we'll be left with x cubed. And the same thing here, natural log of e to the power 8t, the bases match, we'll be just left with 8t. Okay, so these are all examples I wanted to show you today. It took us about half an hour. Again, sorry for not being in class. I hope you'll find these helpful. All right, let me know if you have any questions.